Okay, we're going to continue our discussion with exponents and radicals by now turning to radicals. And first, to kind of see where radicals fall as an operator, we're going to review our operator table. So we start out operators with addition and its opposite, subtraction. And then we build on that with repeated addition, that's multiplication, and its opposite is division. Exponents are repeated multiplication, so they're more sophisticated than multiplication, and then their opposites is radicals. So that's what I'm wanting to emphasize here is, first of all, remember that exponents are repeated multiplication, and more specifically for moving into radicals is this idea that radicals are the opposite of exponents, or radicals undo the exponent or undo the power that we were taking before. Let's look at this with some numbers so you can see what I'm getting at. First, we'll look at it using multiplication and division. So with multiplication, we have that 2 times 3 equals 6. And since division is the opposite of multiplication, that means we can start where we ended and go backwards and end up where we started. In other words, if 2 times 3 equals 6, then 6 divided by 3 equals 2. So notice here that what we started with in multiplication is what we're ending with in division, because division is the opposite of multiplication, meaning it gets us back to where we started before we multiply. Now I'm expecting that you guys understand this relationship between multiplication and division, and I'm using it to then help you see how radicals behave as the opposite of exponents. So let's look at it with radicals and exponents now. With exponents and radicals, we could start with something such as 3 squared equals 9. And then the radicals are going to undo that. In other words, they're going to start with the 9 and get us back to the 3. Start with what we ended with and get us back to what we started with before we applied an exponent. So with that, we have that if 3 squared equals 9, then the square root of 9 equals 3. Now here, when we write a square root, we don't usually write the fact that it's undoing a square, but if we were to write it, we would write it right there above the check mark, so that you can see that when we have that square root symbol, it's going to take the number underneath the radical and unsquare it. Take away the squaring action and getting us back to what we had before we squared. So in that way, it behaves just like the exponents and radicals behave just like multiplication and division in that they undo each other, cancel each other out. So let's look at another one here that isn't a square. So let's say we have 2 to the third, and that equals 8, because 2 times 2 times 2 is 8. So if that's true, then we have to have a radical that will undo that 8. But it wouldn't be a square root, because this time we're canceling out a 3 and not a 2. So what we need there is to write a 3 above the check mark. Okay, so that number above the check mark is indicating the type of exponent we are doing the opposite to, or that we are undoing. So then, if we're undoing the cubing of 8, then that's going to bring us back to a 2. And I know that because it's sitting right here in front of me. We'll look at ones when it's not sitting in front of us and how to figure it out. But right now I'm just wanting you to see that when I put a check mark over a number like that and write a number here, then that number is telling me what type of power I'm undoing, or what number I'm going back to before that type of power was applied. Let's look at some vocabulary now. Alright, so I have my cube root of 8 that I just showed you, and here I said we have to write this 3 above the little check mark to indicate what kind of power we're being the opposite of. That number that's written above the check mark is called the index. Okay, and the check mark itself is called the radical sign. just like an X, so to speak, is the multiplication sign, and this little wonky guy here is the division sign, the radical sign. It's little, I guess they were running out of ideas on signs you could put between two numbers, so they went with this check mark thing. So you have that, and then we have a name for the number that's under the radical sign. The actual name for that is called the radicand, but I really don't use that word. That's technically the right word for it. What I usually say is the argument. Argument, it's a more generic word. Argument is anything that's inside of a math machine, and so it's how I learned using the language, and so that's what tends to come out of my mouth. Both of them are acceptable. It's just radicand is specific to radicals, whereas you can have arguments for other types of math that we will do and look at. And so I tend to use the word argument for radicals as well as other things. So I just wanted you to hear some of the language so that as we go through I can use that language to help explain it. It's good to have nouns to refer to objects, and that's what the vocabulary is about in math, is so we can not call things this guy and that thing, and we'll have like 3 different this guys and we won't know what we're talking about. So the specific nouns, specific vocabulary helps us know which specific math object we're talking about at any given time. So now that we have that down, let's do a few examples. Alright, we're going to start here with example 4, and our directions are to evaluate. Notice I'm starting with 4 because this is continuing from our discussion of exponents. Altogether, the whole lesson is exponents and radicals. So we're just continuing our number from when we were talking about exponents. So evaluate just means to find what number is the square root of 36. And you may know this because you've worked with it before, but just to make sure we're all tracking, 36 is what we want to think of is what number did we square to get 36. So that's the question in your mind, is what number squared, because it's a square root, equals 36. Kind of like when you're doing division, you have to think about the multiplication it came from to get back to the answer. So the number that you square to get 36 is 6. Here it would be helpful if you know some of your basic squares, basic cubes, just the smaller ones, and you can also consult your calculators on these, that's okay. But it is important, whether or not you're using your calculator, that you understand where that 6 is coming from. But that's the number that's multiplied times itself to get 36. Okay? Let's look at another one. Alright, let's check out the 4th root of 81. Now you may know off the top of your head what thing is multiplied times itself 4 times to get 81. So here, that's what we're asking, is what number to the 4th power equals 81. And if you know that off the top of your head, that's great. But I'm going to show you a technique for figuring that out if it doesn't come to you off the top of your head. And what we're going to use to figure it out is factor trees. So to make a factor tree for 81, you're just going to ask yourself what divides into 81 evenly. And you could come up with any number that divides into 81 evenly. For me, the first thought is 9, because I know off the top of my head that 9 times 9 is 81. You might have thought of 3. Whatever, it doesn't matter which one you come up with. Anything that divides into 81 evenly, except you want to stay away from 1 because you just get back to 81. It doesn't really break anything down. So we're just trying to break apart the multiplication. Now you may think, wait a minute, that means that 9 squared is 81, so I can square root it. But you have to keep in mind that we're not square rooting, we're 4th rooting. So we need to know what 4 things multiply to be 81. So then we want to break our 9s down. They break down into 3 times 3, both of them. So whatever's at the ends of the roads here, those will multiply back together to give us the number that we had when we started with. So 3 times 3 times 3 times 3 is 81. In other words, the 4th root of 81 is 3. So you can break down into the pieces to see how many it is that you're looking for, or what it is that you're looking for. So in both of these examples, there was a number, a nice pretty whole number, that this worked out to be. That's not always going to be the case. We need to be able to do ones where it's not just going to come out to a nice pretty whole number. In the ones that we did here, A and B, both of these can be done on any scientific calculator, and it's okay to use your scientific calculator for that. So what I want to look at now is what we do when it doesn't actually work out, that there's not really any pretty number that we can get back to when we're using radicals. To see what I'm getting at, let's consider the square root of 3. So the question is what two numbers multiplied times themselves would give us a 3? So that's what we're wondering, is what squared equals 3. Now if you punch that into your calculator, you're going to get something like 1.732, it goes on, 050, it goes on. It actually goes on forever. And the decimals will never repeat. This is what's called an irrational number. Alright, so you are not going to give the decimal answer unless you're asked to approximate and round to a specific value. So very rarely will I want you to plug this into your calculator and give me this decimal answer. Only when the directions ask you to approximate and round to a specific number of decimals. So that may leave you asking, what am I supposed to say? Well, with the square root of 3, what we actually say is that it's just the square root of 3. We call this the exact answer. And what's that saying is that there's not an integer that this goes back to, and so we're just going to leave it in square root form, because in square root form I know exactly what it is. Once I move to decimal form, I end up having to round off because I can't write a decimal forever, and so then it's no longer exact, it's an approximation. So unless asked to approximate, you're always going to give the exact answer, which means leaving it in the square root if it doesn't square root evenly, or leaving it in the cube root if it doesn't cube root evenly, and so on. Let's look at an example so we can see how this ends up looking when it gets mixed in with other numbers, and also how to figure it out. Alright, example 5, we're still evaluating, and our number here is the square root of 12. And like we saw with the square root of 3, there's not a number there's not an integer times itself that gives us 12. 6, our brains may think 6, but that's not taking the square root of it, that's dividing it by 2. So you don't want to confuse multiplication and division with exponents and radicals. So, but that doesn't mean we stop here. We can be a little bit more tenacious about that, because when I'm looking at 12, I know that there's other numbers inside of it. What I mean by that is 12 is 4 times 3. 4 times 3 is an unsimplified way of writing 12. And so I can think of the square root of 12 as the square root of 4 times the square root of 3 separately. Alright, and the benefit of doing that is I can square root 4. The 3 is what's causing the problem. So we break it down to square root what we can square root and leave the problems as still expressed as square root. So this becomes 2 and then the square root of 3. And those are being multiplied, so we don't write the dot anymore, but that's 2 square roots of 3, or 2 times the square root of 3. And that would be our final answer on that. That's when we evaluate it, we're looking for a value, and that's a funny looking value, but it does work. And if you do the square root of 12 on your calculator, write that down, and then clear it out and do 2 times the square root of 3 on your calculator, you're going to get the same number out of your calculator, the same decimal approximation. So it does work like that, but when you're doing these radicals that don't perfectly square root, you have to break them down and do the radical on the parts that can be perfectly square rooted or cube rooted and so on, and then leave the rest of them alone. Let's look at a different example. So now we have the square root of 54, and now I made the number quite a bit bigger because you may not be able to look at it. Like I could look at the 12 and be like, hey, there's a 4 hiding out inside of there. With the 54, you may not be able to do that, and you may, and that's great if you can. But if you can't, what you can do is resort to your factor trees like we saw in the previous example. So I'm going to go over here to the side, so it's not in the way with the work. I kind of consider this your thinking on paper, so I put it over to the side and call it side work. Because it's just thinking, trying to figure out what I need to do over here to make my problem happen. So again, with this, we can break it down into anything that 54 divides out to. I know that 2 goes into 54 because it's even, and then when I think through that process, I'm going to get a 27. Those may not be the numbers you thought to break it down into, but that's where my brain went, so that's what I did. Now 2 doesn't break down anymore except into 2 and 1, which isn't helpful. So I'm going to focus on breaking the 27 down. It breaks down into a 3 and a 9. And I just keep going until I can't break any of the numbers down anymore. 3 is done, but 9 breaks down into 3 and 3. So if I take the ends of the roads there, and do 2 times 3 times 3 times 3, that will give me the 54 that I started with. But the question is how do I digest this information to figure out what the square root of 54 is? Remember, we're square rooting, so we're undoing squares, and all this stuff is being multiplied. In other words, the end of the road over here is 3 times 3 times 3 times 2. If I wrote it out, you don't have to write this out. This is just me trying to help you see what's going on. So all of those ends of the roads there are being multiplied. So then, thinking in terms of squares, because we're square rooting, I can reassociate the first two 3's as 3 squared, and then I have a 3 times a 2. Okay, I wrote that wrong. It should be 3 squared. Okay, so I made these two 3's into the 3 squared, brought that 3 down, brought that 2 down. Alright, so the square root will undo that 3 squared, and there's nothing we can do with the 3 times the 2. I'm going to write this out really explicitly, and then I'll do it again to kind of show how I would do it once I get the hang of it. So our 3 squared is actually 9, so that's the square root of 9. And then we have the square root of 3, and then we have the square root of 2. Let me show you where that stuff came from and what to. The 3 squared is the 9. The 3 is this 3. And the 2 goes with that. So that's where all those pieces and parts came from. So I'm square rooting what I can square rooting, and the things I can't square root, I'm leaving in square root form. Okay, so now I'm going to write this out. We got square root of 9 is 3. The square root of 3 is one of the ones that we can't actually do, so we leave it as the square root of 3. And the square root of 2 we can't actually do, so we leave it as the square root of 2. And then what we do is we don't want to leave those separate, so we go ahead and put the 3 and the 2 back under one square root. And so we get 3 square roots of 6 as our final answer. So if you take in your calculator and you put in the square root of 54 and get out the decimal for it and the square root and 3 square roots of 6, those will give the same decimal approximation. Now here, what I wrote out here, I wouldn't actually write it out like this every time. This is just me breaking it down so you can see where all the pieces and parts are coming from and going to. Now what I'm going to do is I'm going to draw a squiggly here, and I'm going to do it kind of the way I would do it once I got the hang of it, once I'm understanding the patterns and where things are coming from and going to. So first of all, I wouldn't write this multiplication out over here. I can see that multiplication inside the factor tree. I don't need to write it out. I was just doing that to emphasize that it's multiplication. And then the next thing is I know that I'm undoing a square because I have a square root. And so in my factor tree, I'm going to be looking for pairs because any two numbers that are the same represent something that got squared. So over here in my factor tree, I can look, I have a pair of 3's, so that pair of 3's is a 9, which I can square root completely. I can even see, you can't always see it, but in this one I can see that it came from a 9. That won't always be the case with these. But those two 3's at the end of the road represent a 9, which I can square root. This 3 doesn't have any other 3 to partner with, so it's a single 3, and this 2 doesn't have any other 2 to partner with, so it's a single 2. And so once I get all that marked up on the factor tree over here, I just know that my square root of 54 goes straight to 3 square roots of 6. So what I did there was I took my pair of 3's that I circled and I went ahead and square rooted them down to a single 3. Then I took my 3 and my 2 that I knew could not square root, and I went ahead and multiplied them back together into a 6 under the square root because I wasn't able to square root them. Alright, so let's go ahead and look at a third example here, part C, so we can get some more practice with this. Went ahead and cleared out all our work on that and just wrote the result so that I could have some room to work here. But I do want to make sure you guys understand I want to see your work. I was just have a limited amount of space on my screen here. So now we're going to be looking at part C, the cube root of 72. So with cube roots, we're looking to undo cubing, but the process is the same for the most part. So first of all, I can't just magically look inside of a 72 as easily as I could magically look inside of a 12 up here. So I'm going to resort to my factor tree magic over here to the side. So 72, we want to figure out what that breaks down into. And I know that 8 times 9 is 72. If you don't, you could see that it's even and divide on your calculator to see how many times 2 goes into it evenly or whatever. You just have to get it broken apart. Now, here the temptation might be to say, oh, 9, I know the square root of 9, I can make that a 3. But don't get ahead of yourself because, first of all, there might be other stuff that we need to look at involving the 8. And secondly, we're not even square rooting, we're cube rooting. So don't get too far ahead of yourself. So what I want to do is go ahead and break the 8 down into 2 and 4. The 2 is done, but the 4 will break down into 2 and 2. And the 9 will break down into 3 and 3. So my ends of the roads are the 2's and the 3's. Once you split a number off, you never look back up to that number because, for example, here these two 2's and the 4 represent the same value that came out of 72. So you only look at these are called leaves because it's a factor tree, and these are the ends. I don't know why we don't call them roots, but they're called leaves technically, so the tree's upside down. Anyways, so going back over here, our index here is 3. So this is where it's different, slightly different than what we did in our previous problem. So here we're looking for sets of 3. All of this stuff, all of these leaves over here are being multiplied, and so these 3 2's would be a multiplication of a cube that I could then cube root. But my 3's don't have a set of 3's, so they're not going to be able to be cube rooted. And so then that gives me the result, the 3 2's, which is really just this 8 up here. I cube root and make that a 2. The 3's I can't cube root because I don't have a set of 3 of them. And so I multiply them back together and make them a 9. Alright, so that's the process. You got to be a little patient with yourself getting your factor trees broken down, and also remembering that your index sets the rules of the game. So if it's a cube root, you're making sets of 3's. If it's a square root, you're making sets of 2. If it's a fourth root, you're making sets of 4. Anything that doesn't perfectly group in those sets can't be, I think I'm making this word up, but can't be radicalized. And so then it has to stay under the radical. And I just, as I was talking, saw an error that I made. That's on there. You got to copy your index over. So I hadn't done that. So make sure when you do this, you're copying your index over, because it never changes from the cube root to the square root. So our final result there is 2 times the cube root of 9. Alright, go ahead and work some practice problems on those and see how you do.